Welcome back to our series on introductory statistics. I'm Mark Ledbetter. This is lecture video 24, part A. We are in section 7.3, part 6, and I think this should be part C. So sorry about that. Okay, so last time in the videos by some other people, we have found how to find a raw score when we're given a probability. So we're given this probability. Let's say that x equals 0.2, x less than a is equal to 0.200, and we want to find the value of a, which is a raw score. And so we first have to find the z-score that goes with this. And so since this is a less than, we'd have the 0.2 down less than some value, let's say z1. And this would be 0.200, and so we'd have to look up this z-score here in order to find the raw score. So when we look that up, we'll find it's a negative 0.84, and then to get a will equal x, which in that formula is mu plus z sigma, and then we'd have to plug in mu. In this case, we had mu was 50 and sigma was 1.5, and so we plug that in and we have 50 plus, but z is a negative 0.84 times 1.5, and a plus times a negative is a negative, so this is 50 minus 0.84 times 1.5, and that gave us what, 4874, I believe. 50 minus 1.5 times 0.84, yeah, 4874. And then we did the same thing when we wanted to know a score and we were given a probability bigger. And so, for example, if I give the same probability, then we have b in x. This is what we're trying to find, and the 0.2 is bigger than that, and this was 50. And we want to know what is b. But again, we have to go to the z table and look at it. And for that 0.2, we have to find the z-score that goes with this. And we can't find, if we look at this, we'll find the wrong value. So we need, the table has what's less than. So we look up 0.8. So 0.8 and 0.2 add to 1. The total probability in any probability distribution is 1. So when we look up 0.8, we find that b is equal to positive 0.84. Here, I'm sorry, z, not b. Z, whoops, it's not b. So z2, let's say, is equal to positive 0.84. And so then we'd say that b is equal to x, which is mu plus z times sigma, 50 plus 0.84 times 1.5, which gives us 51.26. Okay, so this is the value of b here. All right, so that's some review. Today we're going to look in this video at a little more complicated for most students thing, but it's really it's really not, as long as you understand the problem. So we want to find values, not one value, but values or raw scores if we are provided probabilities, and this again is an inverse type of problem like we just showed in the review. So how to find two values in the middle of the distribution when we're given or provided a probability. So let's look at an example. I took this example from some of the videos that you saw recently that are linked to the Moodle page, and this is from a YouTube channel of Patrick JMT. So I've linked in some of his videos to the Moodle page because he did a good job of explaining how to do those problems. Unfortunately, he didn't have one exactly like this, so I hope he doesn't mind me, for free, of course, putting this out here for you. So I hope this helps. So scores on the verbal SAT test in 2002 followed approximately a normal distribution with a mean of 504 and a standard deviation of 111. I want to take a minute now and caution you about this notation, because there are two widely accepted notations, and there's no way to tell which one they're using. In this case, they're using mu and sigma, but it is in statistics circle, it's more common to use mu and sigma squared, which is the variance. So which one is it? So that's why I've been very careful to say that, well, I didn't in this one, but I'm going to be very specific that this is sigma that we're using here. I'm not sure which the book does, but in these videos by Patrick JMT, they were this way, so I have written out that. Okay, so scores on the verbal SAT in 2002 followed approximately a normal distribution, mean 504, standard deviation 111, and so between what two scores were the middle 80% of all students taking the SAT verbal test? So when we're asking questions about percentage and we're saying of all students, by implication, we mean the middle part, okay? Unless we say less than or greater than, we're in the top or we're in the bottom or something like that. When we say, oh, we want to know between what two values are 80% of the students, we mean the center, that they're in the center. So I've drawn a picture here for us, two pictures actually, and this is a very good idea to do, okay? So we have the mean, I have x over here, I've put the mean in here, and then I've drawn the normal distribution, and I've put the 0.8, the 80%, and I labeled it in the middle, and I've put A over here and B over here. So what we're trying to find is we have the probability that x is between A and B, that is given to us as 80% or 0.8. Okay? So we want to find what's A and what's B. What are those raw scores that go with this? So again, what we do is we go to our z-table, because that's where we can use probabilities and get z-scores, and if we have the z-score, then we can use the formula x equals mu plus z times sigma to figure out these raw scores. But we have to have a z-score to do that. So if we're putting this in the middle, remember that the normal distribution is symmetric. And so if I could draw this symmetrically, 0.4 would be over here, and 0.4 would be over here. And you could say, well, how much is left over on each half? That's got to be 0.5 total. I'm going to have 0.1 over here, and I have 0.1 over here. Those four numbers have to add up to 1. The other way to figure this out is to not look at it as a half, but to look at it on the whole, and to say there is left over, or remaining, is 1 minus 0.8, which is 0.2. So equal amount in each tail. So 0.2 divided by 2 equals 0.1. Notice I'm putting 4 decimal places here all the time for the probability. The reason I'm doing that is because that's what's in the table. So let's go find a table. And so I'll have to go back here and search for it because I forgot to do it ahead of time. So here's the z-table. Let me clear out the markings from last time so it doesn't confuse us. And so I'm looking for 0.1. This is the value below negative z1. Now why did I use negative z1 and positive z1? Again, I said that I want something in the center, and we have a symmetric distribution. So the distance here from mu to A and the distance from mu to B, these have to be the same amount, the same distance. And if they're the same distance, then that means down here that the distance from the two z-scores from the mean, which is 0, those have to be the same as well. And and we have 0 in the middle here, so that means that z1 is the negative z1 here. This value is the negative of this value because they're the same distance away from 0. That makes them the same number, but one with a negative sign, one without. So I'm going to look up the probability that's closest to 0.1000 in the table. And when I do that, I'm looking inside the table, so I need to be on the negative side because those probabilities are less than 0.5. And here, sorry about that effect. So here is the value that's closest to 0.1. It's 0.1003. The next one is 0.0985. This one is 0.0015 away. This is only 0.0003 away, so it's closer to 1. So I'm going to use the z-score that goes with it, and that is going to be negative 1.28. The 8 is up here. So negative 1.28. So negative, and again I forgot to do my pen. So negative z1 is equal to negative 1.28. So this is negative 1.28. That means z1 is going to be positive 1.28. And now I can find a and b. So a is equal to mu minus z1 sigma. Why did I change this to a minus? Because I'm going to use negative z1. So let me be a little more specific here. So I have a is equal to mu plus z sigma. I'm going to plug in for these. This is 504 plus, but this is a negative 1.28 times sigma, which was 111. And so this gives me, this becomes, this positive and this negative, they become negative. So 504 minus 1.28 times 111. All right, so the sign of the z changes that sign. So it determines if z is negative, we're going to subtract. If z is positive, we're going to add. Minus 1.28 times 111. This is 361.92. So up here, I'm going to clean this up a little bit. So A is 361.92. Now, I could round this to a whole number. I'm just going to leave it like that. Obviously, you can't make a 361.92, so you might round down and say between 361 and whatever to get the actual scores. You might say that's just rounding error and it's really 362 and that's close enough. It depends on your perspective there. So that's for a little more advanced topic. So mu plus z sigma for B, but now this is going to be 504 plus 1.28 times 111. I want to point out that this value, which we're adding to mu, is the same as this value that we subtracted from mu. And so we're going to be the equal distance away from mu, as I said. So we've got 504 plus 1.28 times 111. And that gives me 646.08. So B is 646.08. All right. So the answer to this is, my answer is between what two values is going to be 361.92 and 646.08. That is the answer to the question. All right. So I want to do a bonus question here and go through this again. Obviously, it's making the video longer than 15 minutes. I apologize. But if you understood the first question, you'll understand this one. If you didn't understand the first question, I encourage you to stick around and watch this part. So I took this out of our book. The lifespan of a rechargeable battery is the time before the battery must be replaced because it no longer holds a charge. And it says one tablet computer model. I never thought of a tablet as a computer, but it really is, I guess. So one tablet computer model has a battery with a lifespan that is normally distributed with a mean of 2.3 years and a standard deviation of 0.4 years. So using the notation normal mu sigma, I could write this as normal 2.3, 0.4. Okay? So I've written mu and sigma down here. And here's the question. We want to know the range of the lifespan that includes 70% of the batteries of this specific tablet. Of course, we want the central or middle 70%. So we want to know the range of the lifespan that includes 70%. So 70% of the batteries last between what value? Between this value and this value. How long? Okay? So I hope that kind of makes some intuitive sense why we would use the middle here. So again, I've drawn some pictures, and I have X here, and I put the mean in the middle, and then I have A and B. So we're looking for the probability that X is between A and B, and that is 0.7000. Okay. Moving my tablet, so that's what the scratching sound is. All right, so I'm going to divide this up and say this is 0.35, and this is 0.35, and I need 0.5 on either side, so this is going to be 0.15, and this will be 0.15, and that added together, that is going to give us 1 if I add all 4 of those probabilities, or if I add this and this, those 3. So if I add those 3 together, I get 1. Of course, 0.35 and 0.35 add up to 0.7. And so again, I have a negative Z1 and a Z1. So if I find one of these, I know the other one. I don't have to do it. So since I have the 0.15 down here, that's what I'm going to look up in the Z table. I'm going to try to find the probability or area that's closest to 0.1500. So let me clear off from my last example. And 0.1500, so I have 0.14, let me turn on my pen, 1492 and 1515. So this is 0.0015 away. This is 0.0008 away. So I'm going to use the 0.1492, and that corresponds, that corresponds to a negative 1.01234. So, yes, 4. Okay, so if I pull this down and then scroll back down, we can see 0.1492 is the closest, and that gives me a negative 1.04. 1.04. So this is going to be a negative 1.04. This is going to be a positive 1.04. Again, they have to be the equal distance away from the mean. And so now with that, I can find A and B. And so A is going to be mu plus Z sigma. But Z here is Z1. So this is A equals 2.3 plus a negative 1.04. times 0.4, our standard deviation. And so this becomes 2.3 minus 1.04 times 0.4. And that is 2.3 minus 1.04 times 0.4. 1.884. Now B, and let's look at what this value is. So 1.04 times 0.4, this value is 0.416. So now let's look at B, and that's going to be mu plus Z1 sigma. So this is 2.3 plus 1.04 times 0.4, which gives me 2.716. So again, this is 0.416 above the mean. So this value is this much above the mean, which is 2.3. And this value is this much below the mean. So we're an equal distance above and below the mean here. And so A is 1.884, B is 2.716. Now, I have had students who thought that because it was true for the z-scores, that this value is the negative of this value, that the same would happen here. But that doesn't make any sense. If you find this value and it's 1.884, this value that's more positive, that's higher than that, is certainly not negative 1.884, is it? And since the mean is 2.3, if I find this value first, this value certainly wouldn't be a negative 2.716 because we're not centered around 0. The reason it works in the z-table is that the mean is 0. Okay, so we have found the solution to this problem, 1.884 and 2.716 years. Okay, that's the answer. Okay, so don't forget to scan in your lecture notes before midnight, the date listed on the course calendar. If you need to update your formula sheet, then do so. If you have questions, come to virtual office hours. If you can't do that, email me, but send me a picture of your work and of the problem because I might not have access to the problem wherever I am, and I will be able to help you a lot quicker. So take care of yourself, and we will see you next time.